Welcome back, gang. It is day 101. We had some awesome comments from the previous day, some pretty legendary comments. I didn't get a chance to respond to because it's just been flowing in, but it's just been really awesome to see, to be honest. So very, very immensely grateful. Yeah, and I don't even know what to do or what to say, but we're going up. So shout out to Thomas Wong. Been there, been the homeboy since forever. Silicon STEM Libraries. Thanks for dropping the comment. I promise to respond. Today we're actually starting slightly late, and we're actually going to do 30 minutes today just because I'm a little bit under time. So we're going to be doing 30 minutes, and I'm going to be jumping into it pretty quickly just because, yeah, it's... Unfortunately, I ran out of time earlier, so we're going to be doing a little bit of a shorter session, but like we say, it is a necessary evil sometimes. Also, my IDE and on LeetCode seems to be stuck in light mode. Okay, so it looks like some of it's going to be dark and some of it's not going to be. That's unfortunate, but we're just going to jump into it. So I'm going to try and solve as much as we can this time remaining, even though it's all white. So apologies for that because it's burning my eyes looking at it, so it must be burning your guys' eyes. So given the root of a binary tree, return all root to leaf paths in any order. So given the root of a binary tree, we want to return all root to leaf paths in any order. A leaf is a node with no children. So I'm presume that this will return two paths. So you have root 1, 2, 3, null 5, and the output is 1 to 5 and 1 to 3. Interesting. Interesting. So I'm off the bat. This is the number of nodes in the tree can be 1 to 100. I'm definitely thinking from here we're going to use a DFS. Yeah, I'm definitely thinking a DFS here. Maybe if we start here at 1, we go left, right, then we go right, and the DFS, we could just do in order, I guess, since we can return them in any order. So do L, can't go L, N, R, R, and then here we see that we have no children. And then if we end up having no children, we could add it to a path. So I'm thinking that could work. I feel like we didn't think through it enough. So if we start at 1, and we go left, right, 2, can't go left, so we go N, go R. But I'm thinking, I think as soon as we enter into the node, we could have a path. So maybe we could, if we step out a basic function, the parameters it would take would just be DFS. We definitely pass in a node, an array of the, or we just call it paths, and then we could have something like current path. So if we did that to start, our current path would include 1, right? We'd go to 2, our left child. We'd add 2 to the path, right? We can't go left. We can go right, so we'd call it with right. We'd add 5 to the path. And then we check if it has children. If it doesn't have any children, then we'll add the current path. And then we should be able to propagate back up to 1 and do the same thing. For some reason, I'm thinking current path here could get kind of tricky. Propagate up to 1. So if we did L and R, we'd start at 1, we'd go left, right? Try to go left, we can't. We'd add 1. 1 would already be, or I guess we could add 1 to the path on entry to the current path. Then we'd add 2 to the current path on entry. We can't go left. We're not going to do anything for N. So we'd go right. On entering 5, we'd add 5 to the current path. We could check if it has no children. Has no children, so we'd add current path to paths. Which should take us all the way back up to 1. Would take us all the way back up to 1. This takes us, let me check something. Yeah. This would take us all the way back up to 1. The problem being, though, when we get back to 1, current path would now have 1, 2, and 5 in it. So we'd need to pop a certain number of nodes off of it, depending on where we return back to. That sounds a little cumbersome. Actually sounds a little cumbersome. I guess we could just keep track of how deep we go. Or I guess we could pop nodes off until we have the same node again on current path. It doesn't say that any of the nodes are unique, so we couldn't really do that. Up to 1, 2, and 1. Yeah, I don't like this approach. This approach is DFS. The problem being backtracking. I'm sure this is, you can do this with DFS. I think just the way I'm used to using DFS, I think. I think let's try. I think there's definitely a way to do this with BFS. It seems too BFS-y. Well, if we want the short, we typically do paths with BFS. So I think you could do this with DFS. Maybe it's a native BFS solution. So I think this reads much simpler with BFS. So we just want a path, you know, for every node. So we just want to know. We just want a path. We just want all the paths that go from a root to a leaf. So a node with no children. So we could just do BFS. You start at 1, visit the children, right? And we don't have access to a deck, so our algorithm would be very, very slow. We might get TLE, but what we could do is in the queue, we could just keep track of the current path. For a node, and if we ever end up at a node, a current path for, let's see. So for example, we start at 1, right? We'd add these 2 children on, 2 and 3. So now you have 2 paths going, 1, 2, and 1, 3, right? And the next node that they should visit is 2 and 3. So we pull 2 off, can't go left, so we go 5. Now we have another element on the queue, which is 1, 2, and 5. Right, we actually visit 5 now. It has no children, so we'd add that path, and then we do the same for 3. So I think let's try a native, BFS solution. So the goal here is you would have a queue. Unfortunately, we want a deck, so we could have constant shift or removal from the front. That's just not going to be possible. So we're going to add, our queue is going to be an array of tuples, where the first value will be the node and the second value will be the path so far. So should our root start with the path of itself? Let's see. If we started with the path of itself and then we pull it off the queue, right, we're going to visit its children. So when we visit its children, we push the child onto the queue into the tuple, and then what would we push? The node that we're currently at. So I would actually say we don't have to do that, because it seems like when we pull the node off the queue, we'll be allowed to update that value. So this is how our queue will start, and then we'll say paths is an array of strings that we'd like to return. We'll say while queue.length is not equal 0, right? We're going to want to say node and current path, right? We're going to take it off of the front. And I think our tree all will have at minimum 1 node in it, so we don't have to worry about the null value to start. Once we have the node in the current path, then we want to visit the children. So we're going to want to do this work for both of the nodes. We'll say node.left, node.right. I think collect can only be done in 1 line. So we'll do dot each do child, and then we'll say if child not equal nil, because it's possible that our child could be nil based on these default default value set for these parameters, which get mapped to class properties, instance properties. If the child isn't null, right, then what we'd like to do is push it onto the queue as a tuple, but the next node is going to be the child, right, and then its path is going to be is going to be cur path, which would be 1. And now we're going to 2, so we'll say plus arrow. Cur path plus arrow. And this is the other thing we want to check. If node.left equals nil and node.right equals nil, right? Then we know that this is the last, though we know that this node is a leaf node. So if that's the case, what we'd like to do is say final path equals cur path plus arrow wait, I think we're getting into the weeds here. If we're visiting the next child, we do q dot push child cur path. Well, cur path has nothing in it, so we're just gonna have a bunch of arrows. I think what we want is node dot val dot 2s plus arrow we should put 1 arrow, and then when we visit 2, right, we wouldn't visit left, we visit 5, we'd now add 1 arrow 2. The next iteration we visit 5, both children would be null. We'd say 1 arrow 2, we'd say cur path plus arrow node dot val of 2s. Then we'd say paths plus equal final path else we do the work in this loop. And let's just try this really quick on a simple tree with 1. So our queue is going to start with root and an empty string. Our queue is not going to be empty. We're going to pull off node and cur path, which is going to be 1 and empty string. So do its left and right sub children exist? Yes, so we're going to skip this portion. Now we're going to be in the else. So for node.left and node.right, we're going to do some work for each child. We're going to say if child does not equal nil, 2 does not equal nil because it exists. We're going to say q.push the child, which is 2, and node.val dot to string, which is the node right here, 1 arrow. And then we're going to do the same for 3. It's also going to have 1 arrow. Then we're going to pull the next node off the queue from the front. It's going to be 2. We're going to have 2 and 1 arrow. Do both. Is it a leaf node? It's not a leaf node, so we're going to do else. Node.left is nil, so we skip that. We go to 5. 5 isn't nil, so we push onto the queue 5, and that's what I'm missing. Cur path plus node.val dot to s. So cur path would have been 1. Well, now you have to restart again. So our queue is going to start at root, empty string. Both children exist, so we push an empty string plus node.val dot 2s, which is 1 arrow for both 2 and 3. Then we go to 2. 5 exists, So we're going to push on 5 with the curve path being 1 arrow, the current node being 2, adding another arrow onto the queue. So we're going to have 1 arrow, 2 arrow. Arrow. Then we're going to have 3 arms. So we're going to put 1 arrow plus 3 arrow. 1 arrow, 2 arrow. Then we get to 5. 5 has no children. So final path is going to be equal to 2 arrow, 5. 1 arrow, 2 arrow. One arrow, 2 arrow. So I think it would just be curve path plus node.val.2s or 2 string. I'm gonna try with an even smaller tree. Now that I'm thinking, just do 1, 2, and 3. So if we start the queue with 1 and an empty string, right? You take 1 off the queue, the path is empty. Both children exist, so we're gonna skip this. We're gonna do else. So for 2 and 3, we're gonna push on to the queue 2. We're going to push on to the queue 2, right, with curve pass, which is empty, and node.val, which is 1 arrow. So we have 1 arrow. Now we're going to be at 2. 2 has no children, technically, in this made up example. We have 1 arrow with 2. 2 has no children, so final path is going to be curve path plus node.val, which would be 1 arrow, 2. Paths plus equal. I don't know why I'm doing plus equal since this is an array. And yes. And I think even when we have 1 node in the tree, if it has no children, we would just push curve path, which is empty, plus node.val. So let's try this. Oops, I used triple equals, which is JavaScript. So it works for the first case. Works for the other test cases. Okay, so that works. Yeah, so that's always satisfying to see. I wanted to work through it so that I don't just submit code and just keep always submitting code. I feel like I'm not. It just you run through it too quickly. So I think I'm working based off of feedback from my environment instead of actually thinking through the code that I wrote. And so, yeah. I think this is the best way to do it. I think if I have access to both node and child, so I could do 1 arrow, but I think we get into a sticky situation. But yeah, this could definitely be faster. I'm just gonna swap out the queue in my mind because we're just gonna pretend that it's a deck. If it was a deck, then we would, the BFS would be linear time. And the space would also be linear space. What's the worst case? The worst case is that there are n leaf nodes. There are n leaf nodes, all of length n, which is not possible. So I think the worst case would be linear space. But technically, since we're using a queue, actually space would still be linear, I think. Yeah, we're also using paths.push, which at most, we can't have n leaf nodes. So if our tree, actually maybe we could. Maybe we could have n leaf nodes. I want to say space is linear space because of paths.push. Yeah, I really want to say it's linear because of path.push. Our queue technically would give us n squared time because we have to shift elements every time we have to shift elements down every time we take something off the front. That's a bit slow. Oh my god. I just realized why the oh my god. I just realized why the DFS works. I just realized I said it wouldn't work because I was going to use data structure. I was just going to use an array, which would, because it's by reference, all recursive calls would reference the same array. So in a weird way, the array contains state, which is actually a problem. It was actually a problem because we couldn't like automatically continue from where a path branched off. But if you just use a string, when you do construct path with path, when you backtrack, right, when you finish your recursive call and you backtrack up, you've automatically removed the node. Same way as like, you know, if you were going back from 1 up here. My problem was with using the array. If we went down to 2, 5, we had in the array 1, 2, 5. But when you would backtrack up to 1 here, you'd still have 1, 2, and 5 in the array, which was my problem. But if you just had to use by value our structure that wouldn't have that issue. Yeah, that's really interesting. So I got a jet, but short video today. It's about 30 minutes, so we still did our time. So yeah, and we'll do a better talk of what happened yesterday tomorrow. I just had really short time today.